Hello from the Fortronics YouTube channel, and welcome to Building a Wireless Sensor Network with the nRF24L01. And this is part 3 in probably a 5-part series. If you haven't seen 1 or 2 yet, I recommend you watch those first. To wrap up part 2, 2 alkaline AA or AAA batteries in series will work fine for this design because they'll both give you a voltage level to give you enough power to power the design for a couple years or even over a couple years, depending on the batteries you use and the sample rate and things like that. Now, someone provided in the comments section another good suggestion, and this was for some lithium polymer batteries. And so the idea is these batteries, they're a little safer than the lithium ion. You can use one battery. It'll give you about 3.3 volts or even higher for initial charge. And then the voltage drops slowly when you discharge it. So it only has 700 milliamp hours, but the voltage stays pretty good above 3 volts for a while until the battery's pretty much drained. And so this will allow you to use a single battery instead of 2 batteries, and it'll be rechargeable if you want to go that route. And the person who suggested it, I'm sorry, I forget their name right in front of me, but thank you. They also mentioned that they're going to use this along with the original temperature sensor that I mentioned that provides higher accuracy but requires at least 3 volts to be properly powered. That's enough from follow-up from part 2. Let's talk about part 3. So in part 3, we're just going to quickly review the current hardware design. And once again, it's still in draft form. It can still change a bit. I'm going to demonstrate how to use the settings. So you've heard me talk about using EEPROM to store settings, so that way I can use the same code in different modules, and I can go through these settings, set them, and set up each module individually. And I'll talk about what the settings are. And then I'm going to review the current software or the Arduino code. Now I'm going to focus just on the router or end unit or end device software. And in fact, this whole project's focused more on the router and end device design. So that's what I'm going to focus on. I'll have some example coordinator code that I'll provide as well, but I'm not going to go through that. So another note on the software is it's just going to be in draft form. So I'll do it at the end of this video. If you don't want to hear me go through the software, because there is comments in the software, you'll be able to get it from GitHub, and I'll have information on where you can get it. And just like everybody did for part 1 and 2, feel free to add comments for the software or suggestions, anything about the project in the comments section for this video. Okay, let's take a quick look at the hardware design. So not much has changed. We talked about the temperature sensor changing, and I'm still waiting to get these in the mail to get them hooked up. That'll be covered in part 4. One thing I do want to note, and I did mention it earlier, but this pertains to this part. So the idea is we're going to use the EEPROM in the Atmega 328P, and that's basically acts like a hard drive. We can store settings that are there every time the chip is powered up. So that way we can store individual settings for each module but use the same code. And what I did in hardware to access the settings menu, because you don't want to have to go through the settings each time, is first of all, the code can detect if it's the first time coming up, and if it is, it'll automatically bring up the settings menu, which you enter via serial monitor. But if you want to change the settings, when the chip powers up, you'll press this button connected to D8. And this basically pulls D8 to a low and tells the chip at startup, if I push that button when it's powered up, that we want to go into the settings menu, and the settings menu will come up. Otherwise, if this is not pressed and the design is turned on, it'll just go right into normal functionality and pull the readings from EEPROM. So let me demonstrate that for you right now. Okay, here I have my serial monitor up, and I just have some text in here, current settings in EEPROM. Now I have, how many do I have? I have actually 5 different settings. And once again, this code is just meant to be a reference design, so you can adjust it for your use. But I have first the node address. So we talked about the address system for the network library that we're leveraging. So right now I have the node address set to 3. The internal reference voltage, we're using the internal ADC reference, which is a 1.1 volt, but it's not perfect. So what I did is I measured it and I put in this calibration factor. So when I make measurements, I can use this calibration factor for a more accurate measurement outcome. Then there's the battery voltage calibration factor. This is something we talked about in part 2 extensively. And once again, this can be differ because it depends what resistors you're using for the battery voltage divider. So you want to enter that in. Right now I just have it set to 4, which is not correct, but I can change this. Then I have the interval. This is the interval that the wireless sensor board is going to make measurements and report them to the coordinator. So right now I have it set for 1 second. Then I have the mode. The mode is whether we want it to be a router, meaning we can route information from end devices as well as send our own information to the coordinator. And then also I can set it as an end device. And I also have it set up so I can run through these without having to change every one. So I have no end line character set up. So it's asking me if I want to change the address. So I'm just going to say yes. So I typed in a uppercase Y and allows me to enter the address. Now, I will mention, and I hope this doesn't get I hope this doesn't get confusing, is the addressing is done in octal format. And right now I haven't figured out how to read an octal from the serial monitor. So you have to enter it in decimal and then it's stored and printed out in octal. I hope that makes sense, but I'll demonstrate that here. So I'm going to actually type in 9 for the address, which actually is not a valid address, but in octal 9 is 11. So let me do that. Hope that wasn't too confusing. Do I want to change the reference voltage? I won't change the reference voltage. Do I want to update the battery voltage divider? I won't change that. Do I want to update the interval? Let me just say yes for that. And then it gives me some choices. Enter 0 for 1 second, 1 for a minute. So I'll just enter 1. Then do I want to update the mode setting? And I'll say yes, because right now I have it as a router. So let me change it to an end device. So it says 0 for end device or 1 for router. There's a 0. And so after I press enter, it then prints out the current settings. And this is what I was talking about for the address. So if anybody knows how to sort of convert the octal from the serial monitor to an octal, tell me. Because here I change it to an octal and I store it. My reference voltage and battery voltage divider values do not change. My time interval is 1, which is 1 minute, and my mode setting is 0. I'm done the settings, and after I finished and these printed out, the device automatically goes out of the settings menu, and right now it's operating normally. So it's doing a 1 minute interval, and it's transmitting to the to the coordinator. Okay, so that's an overview of the settings. Now I'm going to dig into the code, and like I said, I'll go over the code in detail here. If you don't want to listen to it, you can go to the end and see where to get the code on GitHub. I have comments in it for you. And once again, this is meant to be a draft code, and it's meant to be a reference design, so you can take it and build onto it for your exact needs. Okay, let's get started going over the code. So here's the various libraries that I call in. The RF24 network, and of course the RF24 for the communication, the SPI for the communication, the sleep, and the watchdog timer. This is for my power save modes when it's an end device. And then the EEPROM library I need for storing and grabbing data from EEPROM. It's just a library. So and some of these I'll skip over if they're obvious, but for this is setting up the radio, this is setting up the network objects. I then set up the variables to store the node address and the receiver, or the coordinator, I should say, node address. A lot of these global variables, like B voltage divider, is what's going to hold the calibrated value after I pull it out of the EEPROM. These values are actually for a timer I've set up. So when I'm in router mode, I don't want to go to sleep because I want to be able to pass data. So when I'm in router mode, I actually use a timer to set my interval. When I'm in end device mode, I use sleep and the watchdog timer to set my interval. And you can see some of those variables here. Here's my structure for the payload, and structures are nice because they allow you to define some set of variables. I can store my readings in here and send it to the coordinator much easier. So I just have the temp value, which I send as a float. I grab, once again, this is meant to be example. I grab an ADC, random ADC value. I don't have anything connected to it right now. And then I have the battery state, which is the bowl, and that's what I showed you yesterday. So once again, just a note, you can change this for your application however you want. Let's get into the setup code. So right away, I disable the watchdog timer, which is something the datasheet recommends. I set the analog reference to internal, telling the ADC of the microcontroller to use the internal 1.1 volt reference. When you make a change in the reference voltage, you're supposed to get rid of the first couple ADC measurements. So I have this function where I just burn 8 readings. I set my pin mode for digital pin 7 to output. This is what controls the LED to show the status. I check my node address. This function, maybe I should change the name, but this is actually calling the settings. So when I entered the settings that you just saw, that was this function call. After I set this function, I set my sleep interval times. And once again, this is only really applicable if you're in end device mode. I start my SPI, I start my radio, I start my network. So if we go into the main loop, first I check if I'm in battery shutdown mode. And remember this from the last video. So what happens is if your battery gets real low, the device wants to stay in ultra power save mode. So it just continues to go back to sleep, back to sleep. So what happens here, if it's in battery shutdown mode, nothing happens, and then it just goes right back to sleep. If it's not in battery shutdown mode, we do a network update. This timer variable, this is if I'm in router mode, because if the timer hasn't gone off yet, I don't execute this code. If I'm in end device mode, this will always be true. I set up my payload, and in my payload, I call a bunch of different functions. I call a function that calculates the temperature using the reference value and an ADC reading. I take another ADC reading that's not connected to anything, just for example purposes, and then I call a function that checks the battery voltage. Please note that I'm using an average function, so I don't just make one ADC measurement. I make up 20 of them, and I average them together to get rid of noise. I then create my network header. This is creating a header that gives information to who I'm sending this to, and this is going to be the coordinator. Then I go into an if statement. I write this. There's the header. There's the payload, the size of the payload. I then check, was the transmit successful? If it was, I make sure that LED is off, because we use the LED to signal if we're not connected and we're not getting a good connection or transmit or whatever you want to call it. If it failed to write this over the network to the coordinator, I say else, and what this does, and this is actually like sort of registered commands, but it's easier than writing out the code, is it just basically says toggle the state of digital pin 7. So if it's low, turn it high, and if it's high, turn it low. So that means it will blink on and off if it's not working. Okay, so that's all that's done for transmitting the data. Now we make our decisions on timing it based on what mode we're in. So if we're in end device mode, I always want to make sure the timer's true. I power down the radio, and then I go to sleep. And I have, when you use the watchdog timer, you have certain intervals you can use. So if we want to go to sleep for like 10 minutes, for instance, I use the interval, and then I loop that interval. So I'm going to sleep, I wake up, I go back to sleep, I wake up, go back to sleep for the interval we set. If we're not in end device mode, then we go to this else statement, and this is checking the timer for router mode. Because in router mode, we don't want to go to sleep. We always want to execute this network update, but we don't want to transmit to the coordinator all the time. We want to do it based on the interval we set. Okay, let's take a quick look at some of the functions. So this one was called in setup. This is the sleep interval. This just takes the value that was set in the settings menu or that you get from EEPROM, and it chooses the count setting, which is the number of times the sleep loop should execute, and the watchdog timer interval. So I have it in binary format because that's how I got it from the data sheet. But this sets whether we want to sleep for 1 second, 4 seconds, 8 seconds, so on and so forth. And if we're in router mode, this will set the time interval for our timer. So that's all that function does. It's called every time in the setup menu. Here is the watchdog timer delay or sleep function. And I go over this. I have a series on power saving with the Arduino and using the watchdog timer in sleep modes. So check that out if you want a detailed explanation of this, because I go over in this. But basically, I'm using some of these functions from the libraries I called. I enable sleep mode. I then go to sleep, and this variable sleep mode, power down, is the lowest power sleep mode, basically turns most everything off. I turn off the ADC, I set some registers. Here I OR it with the timer to set the watchdog timer interval. I then reset the watchdog timer. I tell the CPU to go to sleep. So what happens is once this CPU goes to sleep, the watchdog timer, the chip stops doing stuff and the watchdog timer executes. So the code essentially stops here. And then it'll jump to an interrupt routine, which I'll show you at the end. And then I disable sleep mode, turn the ADC back on, and voila, we're awake again. Okay. Here's my timer function. So if we're in router mode, this timer function basically uses the millis function and basically set on the interval, checks if time's up. If not, it returns false. And if it's true, then the loop will execute the measurements and send them to the coordinator. This next function is long, and to be honest, some of this I should probably turn into libraries that I get called in, but I have it in the code for now. But this is the check node address, and this is what's going to do all the serial communication to get the settings. It's going to store them in EEPROM. It's going to pull them out of EEPROM. So I'm not going to go into great detail. You can see the EEPROM functions are pretty easy to use. You just do EEPROM get, and you give the address where you're storing it. The important thing to note here is you have to know the size of the variable. So here I store it in address 1. It's octal, and that means the next address I don't use is until 3, because the next 2 memory slots, which are a byte each, will be taken up by this octal variable. Oh, I should mention too, this if statement, this only executes if it's the first time the chip is powered up, and I do that by checking if there's a 128 stored in address 0, or it does it if digital pin 8 is at a low connected to ground. And remember, I showed you on the schematic, if we press that switch, turns it to a low, it'll go into this settings menu. Then I just print out a bunch of stuff. And once again, you want to keep these strings short because it uses the memory of the chip. If you use too much, you're going to use a lot of your dynamic memory, and it's not good. So I think right now I'm up to about, I'm actually using 63%, so that's actually a lot. So for me, I may cut some of these words down in the future. Okay, once again, this is just going through the answers to the settings. I do some checking to make sure the correct values or applicable values are entered, and if they're not, I set it to some sort of default value. Then what happens is this function is always called, but if we're not changing the settings, all that happens is it calls get EEPROM values, which is another function, and it just grabs the values that are already in EEPROM. And that is this function right here. So it's just getting the values and it stores them in my global variables, so we have them and we can use them in the code. These other functions are related to the settings menu, such as get answer. So I wait to see what the user enters, and if it's a Y, a capital Y for yes, then I allow them, then I return true. If they don't enter a Y, it means they don't want to change that function, I return false. Similar with get interval, that's for setting the sleep interval and the strings that I want to display. Get mode, similar. One thing I will mention is when you're using sleep, you want to be sure that you turn your serial communication off, because serial communication uses interrupts, and you don't want interrupts happening when you're setting your watchdog timer and going to sleep. So just to note, you want to turn the serial communication off when you're using the watchdog timer in sleep mode. You also don't want to use the delay function in Arduino when you're using those modes as well. Okay, get mode. This just burns 8 readings. So when I change my internal reference, I want to get rid of some of the readings. This is a function that converts the ADC value to a voltage. This is a function that based on the TMP36 converts a voltage to a temperature. So I'm just have this in there right now because I'm using the TMP36 for prototyping, but once I get my other temperature sensor in, I'll have to change this. This function averages the ADC readings together and based on how many you want to average together. If you saw part 2, this function basically is doing my battery calculation. So I actually hard coded these in here. I could add them to the settings. I decided not to. You could always do that though. I hard code what a low battery and a dead battery is. And so this was prominently showed in part 2 when I demonstrated the battery capabilities, but this is just checking if I have a low battery or if I need to go in battery shutdown mode. And then last but not least, this is the Watchdog Timer interrupt service routine. That's what ISR stands for. Once again, I talk about interrupts and the Watchdog Timer in different videos, so you can check that out. But just to note, you have to have this in the code or the Watchdog Timer will not work. Okay, that's it for part 3. In part 4, we're going to go over the BOM, the bill of materials, just to review that. We're going to show the temperature sensor in action, and we're going to go over the initial PCB design using Eagle, which I'll use to send off and get a custom PCB made for this project. All right, thanks for watching part 3. I'm going to post the code on GitHub. You should see a note of where you can find it. Feel free to leave comments and suggestions or questions. Thank you for watching.